I'm Qinhong from Zhejiang University. Thanks for your patience. Today I'd like to talk about our work on the security of camera system, which is GlitchHiker, uncovering vulnerability of image signal transmission with IEMI. Specifically, we investigate how intentional electromagnetic interference affects the camera's output and downstream control algorithm. Camera-based computer vision systems are widely used for surveillance systems and self-driving cars. The reliability of these applications is critical and is determined by the captured image. However, numerous work has discovered potential attacks that may fool the civil system. For instance, research has shown that using light, laser, and even acoustic signal can affect how camera capture images and consequently causing incorrect detection results. So how about the other types of interference like electromagnetic waves? We have discovered that the unintentional interference from the environment can induce camera glitches, such as purple stripes overlap across the image. However, none of the work has systematically investigated why this phenomenon happens, and it is also unknown whether these purple stripes can affect the civil system. So from a security perspective, can we intentionally induce and manipulate these glitches? If this assumption works, here is our threat model. The adversary can interfere with cameras via EMI and stealthily falsify the captured image to spoof the computer vision system. We mentioned that there may be three types of attacks: hiding attack where an object disappears, and creating attack where a new object appears, and altering attack where an object is misdetected to another. Having introduced the context, let's delve into the main topic. To achieve this kind of successful attack, there are three research questions. Why these glitches happen, and what is the common pattern of glitches, and how will glitches affect civil systems? To answer the first why question, let's have a look at how a camera-based computer vision system works first. There are four components. The CMOS sensor captures the field of view, which is then transmitted to the microcontroller through a standard camera interface and is processed into an RGB image. Finally, the object detection method detects the car. As mentioned before, the security of camera system has been widely investigated. For instance, adversary can mislead the computer vision system by purposely designing patches on the object, and they can also interfere with images sensor capturing operation. However, the vulnerability of transmission and processing components have long been overlooked, and our work uncovers that the transmission cable acts as a receiving antenna to be interfered by EMI and becomes a new attack surface. Let's shift our focus to an important aspect. Under normal conditions, each image row is packetized in the format with the start of transmission at the beginning, at the end of transmission at the end. The ECC checking and checksum mechanism is implemented to detect and correct transmission errors. The image raw data is transmitted row by row via the standard camera interface, such as the MIPI CSI2. Finally, the microcontroller processes the received raw data and outputs the RGB image. Despite this, when the image transmission cable is interfered by the EMI, numerous transmission errors occur in the packet of row 2, and the microcontroller detects and discards the packet 2 and stitch the rest packets together. And this is when the camera glitch starts to appear. From the first why question, we have known that captured image will lose few rows when the transmission is interfered by electromagnetic interference. Now let's turn our attention to the second point. What is the consequence of missing a row, and what is the common patterns of glitches? To answer this what question, let's have a look at how the microcontroller processes the captured image raw data. The glitch pattern appears because how this image raw data from CMOS sensor is interpreted. For instance, for given a 3 by 3 pixel, as shown in this slide, The raw data appears as 3x3 values, which is mapped to the grayscale of each sensor. The same sensor is arranged in a 9 alternating fashion of green, blue, and red-green sensors, and each sensor measures only one color. For instance, the green sensor measures the green scale and blue and green. So if we don't do anything, we just use the grayscales of that color directly, then we get a mosaicated image. Finally, the real RGB image is processed as a result of demosaicing. For instance, the middle green pixel will use the pixel surrounding it and get the RGB value. So everything on the image processing is done with a prior knowledge of CMOS sensor color arrangement, and each pixel measures a corresponding color. When a row is missing, the microcontroller's prior knowledge of CMOS sensor color arrangement will not be updated, and the microcontroller processes the raw data as usual. Thus, as seen in this image, the red and blue pixels are processed at green scale, and the green pixels are processed as red or blue scales, resulting in a final purple RGB image. Similarly, when a second row is lost in the same manner, the color interpretation is restored, resulting in a colorful stripe overlapping across the image. Numerous color stripes may be induced depending on the RGB values of the source image. As seen in slide, missing rows change the color space of a color checker from the standard to purple-green. For instance, the green region becomes purple, while the red region becomes green. Since previous adversary example didn't consider such glitch patterns, existing computer vision algorithms are not robust to this pattern and can lead to incorrect detection results. The last one we like to investigate is this how question. We designed GlitchHiker attack to demonstrate the security impact of this pattern on CV system. There are two key attack building blocks. The first one is to find the proper injection frequency to perform efficient glitch injection. And the second block synchronizes the injection with the image signal transmission. In this way, the adversary can manipulate the position and width and the number of stripes on the captured image. We have evaluated the effectiveness of a GlitchHiker attack on 8 off-the-shelf camera systems and 4 object detectors and 2 face detectors. This is our experimental setup. The attack results show that all the 8 cameras are vulnerable to our EMI injection, and the GlitchHiker attack can inject stripes at various frequencies. Next, we validate the attacks on these cameras against computer vision system with 2 case studies. The first one on 3 versions of YOLO models and fast RNCN shows that injecting only 1 stripe can hide, create, or alter objects with a maximum successful result of over 98%. And the second case study on FaceNet and Retina Face shows that GlitchHiker attack can hide or create person with a maximum successful rate of over 18%. Furthermore, we have built an attack prototype for less than $14 in order to demonstrate the feasibility of the end-to-end attack in a real-world scenario. To alleviate this vulnerability, we propose hardware and software-based countermeasures. The first one is to shield the image transmission cable, and the second one is to improve the error handling mechanism to deal with packet loss, such as replacing the missing rows with zeros. And the last one is to detect glitch patterns by calculating the color differences. To sum up, we have uncovered a new class of camera vulnerability in image signal transmission phase for the first time. And we have designed GlitchHiker attack, which can intentionally falsify a camera's output images by adding controlled glitch patterns while EMI injection. Last, we call for further research to focus on the security of sensory data transmission channel. That's all of my talk. More details can be found in the paper, and thanks for your listening, and I'm ready for questions.